You've probably seen this happen on a weather map. You're watching a storm move across the country, and then it just seems to fizzle out. But at the same time, a brand new, massive storm just explodes onto the coast out of nowhere. It looks like it literally jumps. Well, that's called a Miller-B storm. And to really get your head around it, you have to completely rethink what a storm actually is.
So what's going on here? Why would a storm just ditch its path and pop up somewhere else? This isn't a simple case of, wind pushing things around. To really understand it, we've got to ask a totally different question. We have to look at this storm as if it's making a choice.
And that's the whole key right there. We're going to look at this entire event not as a mechanical process, but as a system of energy that is actively looking for the absolute best, most efficient path it can find. This is a story about a fundamental law of the universe playing out right in our own atmosphere.
This quote just nails it. We have to get rid of this idea of a failing storm. That's not what's happening. Instead, just imagine a system whose only job is to move energy from hot to cold, from high pressure to low, and to do it as fast as it possibly can. That process? It's called entropy. And entropy is the real star of this show.
Okay, so to figure out why the storm jumps, first we've got to look at the original storm that's kind of chugging along over land. And let's stop thinking of it as a storm. Let's think of it as a machine, an engine that's really starting to show its age. Because at its core, that's all any storm is, really. It's a heat engine. It takes the difference in temperature, that thermal gradient, and it converts that potential energy into kinetic energy, which we feel as wind. It's this beautiful, organized machine for moving heat around. But it's got a big problem. See, as this engine moves over land, it starts to sputter. You've got friction from mountains and trees creating all this resistance. But even worse, the storm's own circulation starts messing everything up. Cold air gets wrapped around the warm core, which kills the very temperature difference that powers the whole thing. It's literally eating its own fuel. From an energy point of view, it's becoming incredibly wasteful and inefficient.
Now, while our inland engine is coughing and sputtering, the atmosphere sees another option, waiting right there just offshore. And it's not just another option, it's a pristine, high-speed, 8-lane superhighway.
The coast is a special place. You have cold, dry air from the land right up against the warm, moist air over the ocean. Think the Gulf Stream. Now, unlike our inland storm, which is busy destroying its own fuel source, the ocean is a massive, stable source that is constantly keeping that temperature difference alive. It's a golden opportunity, just sitting there.
So now the atmosphere has two choices. You've got the inland path, we'll call it the dirt road. It's got high friction, the fuel's running out, it's a really high resistance pathway. But then you have the coastal zone. That's the superhighway. Low friction, unlimited fuel. Now, if you're entropy and your only goal in life is to move energy as fast as possible, which path are you going to take? It's a no-brainer, right?
Okay, so how does the atmosphere actually make this choice? Well, the decision isn't made down here at the surface. It's orchestrated from the top down, by that giant river of air flowing miles and miles above our heads.
You have to see the jet stream as more than just a current of fast-moving air. It's the master controller. It's the conveyor belt that's managing this whole operation. It's the part of the system that actually finds that coastal superhighway and opens the on-ramp.
And the tool it uses is something called divergence. Basically, when the air in the jet stream spreads apart way up high, it acts like a giant industrial vacuum cleaner. It starts sucking the air and energy up from the column below it. It creates this massive exhaust port in the sky that basically screams down to the surface, "Hey, send your energy up here. This is the fastest way out."
So, we have a failing engine over land and a brand new, super efficient exhaust port opening up over the coast. What happens next is not a polite handoff, it is a hostile takeover. This is survival of the fittest for weather systems.
And it happens unbelievably fast. It's like flipping a switch. The jet stream opens that vent up top. In response, the pressure at the surface just plummets. Air from every direction comes rushing in to fill that void. The Earth's rotation gives it a little spin, and bam, you've got a brand new, powerful cyclone.
So this is the really critical thing to get. The old storm doesn't slowly transfer its energy to the new one. The entire energy flow system just snaps into a new, better shape. The old pathway is just abandoned instantly.
And I just love how this quote puts it. The old storm isn't killed, it isn't absorbed, it's just ignored.
The bigger atmospheric system found a better way to do its job, and the old storm is just left behind. It becomes completely irrelevant to what's going on.
And this gives us this amazing new way to think about it. Darwinian weather. The coastal storm forms because it absolutely crushes the inland storm at the job of producing entropy, of moving energy. It wins the competition, plain and simple, and the system reallocates all of its resources to the winner.
So if we zoom out, this one type of storm starts to reveal something really profound about the nature of our atmosphere. It's not just a random bunch of gases bumping into each other. It's a dynamic, constantly changing, intelligent-like network.
Yeah, the atmosphere is acting like a self-optimizing system. Think about that. With no brain, no central computer, it's constantly sensing where the flow of energy is getting sluggish, and it's rerouting that flow down better paths. It abandons things that don't work anymore, all to keep the energy moving.
And this all leads to this incredible paradox. We look at a storm, this magnificent, beautiful, ordered spiral of clouds, and we think its purpose is to create order. It's not. It's the exact opposite. All of that local, beautiful organization exists for one reason: to more efficiently destroy the bigger energy imbalance across the globe. It creates order just so it can create a bigger mess.
And that's really the final takeaway here. What we look at and call chaos is actually a highly selective process. The atmosphere is always making choices. It's selecting the most efficient way to do its job. The Milliby's storm isn't some strange freak of nature. It's what natural selection looks like on a weather map.
Which leaves us with one last kind of mind-bending idea to chew on. We just watched a non-living system, the atmosphere, detect a problem and then reconfigure itself on the fly for better performance. So the big question is, if the weather can do this, what other systems in our world, from economies to ecosystems, are playing by these exact same fundamental rules?